Hello everyone, my name is Anurag and our paper is titled Urban Semantic Segmentation with Low-Cost Coarse Annotation.
Let's begin with the motivation of our work. We know that semantic segmentation requires expensive pixel-level full annotation. Our motivation is to reduce the annotation effort using cheaper coarse and synthetic data. As an example, we have fine annotation on this image as well as coarse annotation. We see that fine annotation has this finer boundary details, whereas the coarse annotation lacks this finer boundary details for faster annotation time. On an average, fine image takes 90 minutes per image for annotation, whereas coarse image takes around 7 minutes per annotation. For our work, we want to utilize this cheaper coarse annotation and get comparable performance with fine annotation.
In this slide, we provide an overview of our approach. We have three different phases, namely network pre-training phase, pseudo-labeling with consistency constraint, and network retraining phase. In the network pre-training phase, we have synthetic data and coarse data. We also have cross-domain augmented data, which is simply an augmentation of synthetic data onto coarse data. We have cross-entropy loss on the labeled pixels of the input images, whereas we have an additional boundary loss on the synthetic data. We train a segmentation network using these two different losses. In the next phase, we have pseudo-labeling with consistency constraint. Our motivation is to obtain correct pseudo-labels for the unlabeled regions of the coarse data. For this, we perform different augmentation of the input coarse data and make sure that the network predicts same pseudo-labels for the different augmentation. After pseudo-labeling with consistency constraint, we have network retraining phase. In this, we use the pseudo-labels obtained from the previous phase and then again train our network as a network pre-training phase. The key components of our method include boundary loss, cross-domain augmentation, and self-training. We explain each of these key components in the next slide. The first key component is boundary loss. We aim to improve boundary level prediction for coarse annotation. We learn these boundaries from synthetic data and aim to transfer to coarse data. More specifically, we match gradient magnitude of ground truth and prediction for synthetic data. The next key component is cross-domain augmentation. Since there is a domain gap between coarse data and synthetic data, we cannot simply use this data together. For this, to reduce this domain gap, we use this class mix based approach. We simply cut paste synthetic class masks onto coarse data. The third key component is self-training. We learn from generated pseudo-labels on the unlabeled regions plus coarse annotation. We utilize augmentation consistency to obtain better pseudo-labels. We also use confidence pseudo-labels for training, for which we use thresholding with a threshold parameter of 0.9. In this slide, we discuss the result of our method. We evaluate our method on Cityscapes and BDD100k dataset. Our baselines is DeepLab v3 plus trained on fine data, which is DeepLab fine with coarse pretraining, which is DeepLab fine plus coarse, and synthetic is DeepLab, GTA, and Cityscapes. We observe that our method, which is red and green curve, outperforms the baselines by huge margin, further with only very less annotation budget. To summarize, our proposed method exploits cheaper coarse annotation for training and performs comparable performance with fine annotation in fraction of annotation budget.